Welcome to this webinar on Total Project Planning and Optimization. The webinar describes two case study applications of the Total Project Planning for Risky Projects approach. The first describes a planned procedure for pressure testing of LPG storage tanks in the Plinarna plant in Slovenia. The second describes the planned overhaul of the cold water system at an ESB station in the west of Ireland. Cold water or acoustic testing for pressure vessels is required every 5 years by law, and so cold water testing may occur more infrequently. As the product, LPG, needs to be emptied and the vessel prepared for testing, the operation is logistically and time demanding. The operational experience from previous tests is also limited due to the absence of the experienced site personnel, as staff changes can be significant within one test period. In this case study at Plinarna Maribor, the cold water procedure has not been undertaken for over a decade. Thus, the testing procedure needs to be reinvented in detail and planned for this rare, complex, expensive, and safety-critical operation. The planning used any past knowledge and information on the duration of the procedure, the occupational and process safety risks, as well as the available resources in order to define and optimize the procedure and explicitly specify safety measures. In order to overcome the uncertainty in organising the test, the procedure, actually not performed before by the current plant personnel, needs to be reinvented. So, how can we help? The approach was to use task analysis in conjunction with 4D modelling of the operation. The task hazard tool was used to document the task analysis and perform a hazard using available information on the planned procedure. Next, the plant site was mapped using photogrammetry and a 3D model built and used for the subsequent 4D simulation. After the task analysis, the initial 4D model was used as a review tool, and the hazard identified issues and documented a list of operability and safety improvement measures. The sequence of activities was then optimized in order to avoid problems and costly delays. Finally, we planned to compare the optimized procedure with the actual implementation to validate the results and approach, but this has not yet been possible due to delays in the planned testing procedure. Here, you can see the process explained graphically. It shows how the process considers iterations applied for the system modelling, safety analysis, and efficiency analysis, and optimization steps. The procedure planners were involved in the task analysis and hazard identification. This provided them with better insight into how to plan and perform the procedure. As a result, two procedure specifications were produced, namely the original and the optimized ones. The optimized was developed from the original, explicitly considering procedural decision points, more logical arrangement of the tasks, and with recommended safety measures and safety criteria to be met. The final result delivered to the procedure planners was the overall optimized procedure consisting of 22 main and 112 sub-tasks. In addition, 26 operability and safety issues were identified, leading to 14 detailed measures specified from the hazard study. Optimization of the duration using a Pareto analysis led to an additional 6 measures, thus in total 20. For the purpose of evaluating the results, the original and optimized procedures were compared in terms of planned duration, delay risks, occupational risks, and process safety risks. The original planned duration of about 15.4 days was by task optimization reduced to about 14.8 days. Considering also potential delays due to possible errors and failures, the durations are about 16.6 and 15.5 days respectively. The assessed monetary values were calculated for categories of production costs, occupational risks in terms of potential lost GDP for an average occupational accident, as well as for the potential process safety risks. Occupational accident costs do not include compensation and medical treatment costs and would likely lead to an average 5-day stoppage. The process safety risks include both immediately observable and dormant or hidden consequences that might be revealed at any time later on. It can be concluded that both procedures are related to considerable risks, and the optimized one provides much lower occupational and process safety risks. The final conclusion is that the study provided solid foundations for the plant management to plan the coming testing procedure in a safe and optimized way. The cost of the procedure development is assessed at about 1 engineer month with a gross salary of €3,000. the reduced values at risk are much higher. The second case study in this area was the planning of an overhaul procedure for a cold water system at ESB. The methodology was repeated in a different context to plan for another rare procedure, this time in a coal-fired electricity generating station in the west of Ireland. In this case, 4 large valves in the cold water system needed to be replaced due to leakage. These valves had never previously been replaced in the 30 years of plant operation, and so there were many unknowns related to the procedure. Additionally, the valves could only be replaced during an outage of 2 of the 3 units in the station, leaving a 6-day window of opportunity for the works. Overruns would incur a significant cost and lost revenues for the plant. The aims of this work were therefore firstly to provide some assurance that the task could be completed in the time window, since any uncertainty about this might mean postponing the works until a longer outage could be secured. Secondly, the work aimed to identify any risks to the safe and timely completion of the works in order to identify mitigations to reduce the risk. The project started with a workshop to elicit the tasks and task timings for the entire procedure. A simple tabletop mock-up of the system and Lego figures were used to help gather the information, which was then represented in an Excel-based task analysis. The task analysis was the basis for the PERT diagram and Gantt chart produced. The information was iterated several times in repeat workshops and individual meetings with key stakeholders until a final stable version of the task analysis was produced. At this stage, a final workshop was held with stakeholders to identify and mitigate the possible risks to the project. Finally, the task analysis and hazards were used as inputs to an Excel-based discrete event simulation, which used the expected, maximum, and minimum task durations to calculate the expected time completion for the procedure and to explore the effect of increasing or decreasing key resources. The analysis showed that the project could be completed within the available time window, but some recommendations and modifications were made to reduce the risks of delay. These included reducing the number of valves to be replaced, thereby reducing the overall complexity of the procedure. The use of additional resources such as a second crane had the potential to reduce the overall time by 7 hours. The process also calculated that a slippage in the start time of more than 24 hours would result in completion outside the available time window. The actual project was completed successfully during the planned outage. Some unexpected corrosion was found in the pipework, prompting additional repairs, but the analysis gave confidence in the time available for those repairs. Comparing the predicted work to the actual results, the analysis showed that the work could be completed in 4 days, but in fact took 7. This was due to the overrunning of another piece of work during the same outage, which took pressure off this job to complete on time. There were some delays to the isolation of the system, and work that had been planned overnight was postponed to daytime. The actual times for each activity were typically shorter than had been estimated, although within the overall expected window. The approach had a number of benefits. Key among them was the early engagement of key stakeholders. The clear planning achieved with their input helped to identify pre-work and mitigations to help the project run smoothly. The analysis also gave the managers confidence in what was possible in the available time window. Comments from the stakeholders involved in the project illustrate how useful they found the process. In summary, total project planning and optimization is a participatory approach to collecting, analysing and reviewing information to de-risk a complex or rare procedure. The approach may be tailored to the needs of different projects, but the main steps involve starting with a workshop to outline the tasks and generate the task analysis. This data is then used to produce an initial project plan, which can be combined with a 3D model to produce a visual simulation of the work. A second workshop is used to identify hazards and mitigations, and these can be tested in a Monte Carlo or Pareto analysis, allowing the procedure to be optimized.